Now we're going to look at isotopes. An isotope was actually the second way that John Dalton was incorrect with Dalton's atomic theory. Dalton's atomic theory first said that all atoms of the same element are identical, and we actually know now that that is not the case. He also said that they were tiny indivisible particles, which we've just spent in the last couple of videos looking at, that there are protons, neutrons, and electrons there, so they are divisible. All that an isotope is an atom of the same element that has a different number of neutrons. Remember, neutrons create nuclear forces which holds together the nucleus of the atom. They are just a part of the mass, and they help to absorb away some of those positive charges. So as we're looking at the neutrons that are there, I always kind of go back to my days teaching kindergarten. And when we look at those days teaching kindergarten, we didn't have glue sticks when I was teaching kindergarten. We had Elmer's glue. And the Elmer's glue that we had was the liquid kind in a bottle. And you always had like two different ends of the spectrum on either side. And then you had the, like, I don't want to say average kid in the middle, but average kid in the middle. The first side, sorry guys, sorry girls, but it was usually a girl. And they would take the glue bottle, and if I use my pen as the little glue bottle here, and let's say that the task was to take these two pieces of paper and glue them together. They would take the glue bottle, and usually it was a girl, like I said, and they would go dot, 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 one in the middle. And then they would put those two together. And then they would take it to the drying rack, and there would be very little glue on the outside of the paper. Then the other end of the spectrum, usually it was a boy, sorry boys, but I'm being general here. That little boy would take their piece of paper on the table, they would take the glue bottle, usually it was a two-handed job, and they would pour the glue. They would keep pouring, keep pouring, keep pouring, keep pouring until they had like Lake Elmer going on here. And once they had Lake Elmer going on here, they would take the other piece of paper and they would put it on top of the other one, and it was floating on top. And then they would pick up their piece of paper to put it onto the drying rack, and it usually did this because it had so much mass on it. They would take it to the drying rack, and it would dry. Now, if the task was to glue this piece of paper to this piece of paper, they actually completed that task on both ends of the spectrum. Just one of them would have a lighter mass than the other one. So when we're looking at the two masses there, one person used more glue than another one. Same thing with isotopes, same general concept. Sometimes when the atom comes together, there was more glue used in one than another one. So you have different numbers of neutrons. So the atoms themselves are all identical. They have the same function, they have the same characteristics. The only difference is their number of neutrons. Because they have a different number of neutrons, they're going to have an overall different mass. So when you're looking at the difference in these isotopes, it is solely the number of neutrons that are present. So some of them use more neutrons than others, so some of them have more glue than others. When you take the mass differences, those mass differences are just because of the different amounts of neutrons that are there, because the mass number is the number of protons plus the number of neutrons. So if you look in this picture here, a neutron and a proton have about the same mass. Underneath this, there's 1,836 electrons is equal to the same mass as one proton. Electrons are insignificant in mass when it comes down to it in terms of the mass number of an atom. So the mass of the atom solely comes from the protons and the neutrons being added together. So when we have the exact mass, when we know the exact mass, we have to give the exact mass. So here in 3 different ways I have oxygen, well actually 4 different ways, sorry, 4 different ways I have oxygen written down. In all 3 of these, this red 17 is the mass number. We know the exact mass of this oxygen is 17. That is different than the information on the periodic table. As you're going to find out in the next video, the number on the periodic table is actually a average, and with that average on the periodic table, it's an average of all the isotopes. So this 17, this one, and this one, these are all the mass number, and that is the exact mass of that particular isotope. This number 8 right here, Sometimes that's given. It's not given very often, as you're going to see in the example slide why it's not given very often. But it's just difficult to type on a regular computer program like Word or PowerPoint or Google Docs or anything. But that 8 is the atomic number if it's ever given to you, and they just give it to you so you don't have to look it up. So this mass number is the protons plus the neutrons, and then this right here is just the number of protons, which is the atomic number. Struggling, sorry. So when we're looking at the periodic table, it's going to give you a mass, or not the mass number, sorry, the average atomic mass. And that average atomic mass is just taking all the known isotopes of that element and it's averaging them together. We're going to figure out how to calculate that in the next video. So the numbers that are given on the periodic table are just averages of all the known isotopes. When a mass number is given, it is the exact mass of that particular atom's isotope. So that one isotope that's there. So we have some more examples here, and again I've got that typed out on a piece of paper. I also have my periodic table, so I'm going to switch over to my document camera here. And when I switch over to my document camera here, it again says to find the number of protons, electrons, and neutrons in the following, and again it's all given. These numbers here are my mass numbers, so NB is niobium, so this is niobium 94 is how you say that. This next one is germanium 75. So when we have the number, it's given in the name on how you speak it. This one is manganese 55. SB is antimony. This is antimony 130. So we verbally say the mass number when we know the mass number, so we know which isotope we're talking about. I'm going to make a chart like I made in the last one. So we're going to find the number of protons, we're going to find the number of neutrons, we're going to find the number of electrons that are given. What we're going to have to do first is we're going to have to look up the atomic numbers. Here it's given on the antimony 130. Unfortunately, the other ones it's not given, so we're going to have to reference a periodic table. This is why typically they're not given. This 51 should actually be right here. It should be like stacked on top of each other. But again, with PowerPoint and Word, they just don't like to have those two variables one on top of the other, so it's kind of difficult to do. So what we're going to do here is we're going to look up the elements. When we look up the elements here, niobium is number 41. Now if you notice, this mass number is 92.90, so that would round up to 93. The particular isotope that we have here is 94. I don't care what the periodic table says if the mass number is given. This number is more important than what the periodic table says. So this is number 41. Germanium, we're going to look that one up on the periodic table. When we look this up on the periodic table, germanium is number 32. Manganese 55, again, I'm going to find manganese on the periodic table. Manganese is number 25. And then lastly, I have antimony 51. Hey, lucky for us, we don't have to look that number up because they give us the atomic number. If you wanted to verify, if you didn't believe them or something, antimony is right here. It's number 51. So we don't have to worry about that. So what we're going to do is first we're going to find the number of protons in niobium 94. Niobium 94 is number 41 on the periodic table, so it has 41 protons. If we have 41 protons, we also have 41 electrons. Now for this one, I have a mass number of 94. I have 41 protons, so I'm going to get the difference, 94 minus 41, to get the number of neutrons. So when I subtract those two values from one another, you end up with 53 neutrons. Mass number is neutrons plus protons, so that's where the 94 came from. Germanium 75, I have 32 protons. If I have 32 protons, I also have 32 electrons. Now for my neutrons, I'm going to take the mass number that's given, 75, minus 32 protons. That's going to give me 43 neutrons. So in this particular isotope of germanium, we know the exact number of neutrons, which is 43. In manganese 55, I have 25 protons because it's number 25. If I have 25 positive protons, I have 25 negative electrons. To get my number of neutrons, I'm going to take my mass minus my atomic number. When you subtract those two values, you end up with the number 30. So 30 plus 25, protons plus neutrons, gives me my mass number, which is 55. Now, for antimony 130, we have an atomic number given of 51. So that means that I have 51 protons. I also have 51 electrons. My mass number is 130. My atomic number is 51. So if I take 130 minus 51, I get 79 neutrons. Ooh, sorry, it's not on there anymore. I wasn't paying attention to my screen. So when we're looking at these values, the number of protons is the atomic number on the periodic table. My number of electrons is the same as my protons. To get my neutrons, I'm going to take my mass number, which is given for that isotope, subtract off my number of protons, and that is because my mass number is equal to protons plus the number of neutrons. So for each isotope, that might be different because they're going to give you the number of neutrons. The protons comes from the periodic table. That's going to give you the mass of that particular isotope. So when you have a mass given, you're going to use that mass. Don't use what's on the periodic table because that does not matter.